All right, let's get started. Today we are going to talk about recursions. These are what we are going to talk about today. First, we're going to discuss what recursive functions are, and then we're going to talk about a special type of recursion, that is mutual recursion. And we're going to have a look at what are the differences between recursion and iteration. And we are also going to have a look at a special type of tree recursion. And I'm going to present some examples and then summarize this lecture. All right, let's talk about recursive functions first. So what are recursive functions? In general, recursion means to define something in terms of itself, such as the definition of a tree. So when we define a tree data structure, actually it is another type of data structure we're going to talk about in the following lectures. When we define a tree, we define tree in this way. A tree consists of a root node, which is connected to the roots of 0 or more trees. So when we define a tree, the definition of tree contains the term tree. So this is how we define something in a recursive way. So basically a tree is looks like this. So a node is connected to other nodes like this. In computer science, a recursive function is a function that calls itself in the body of that function. Then why do we care about recursive functions? Recursive functions aim to solve given problems by splitting them into smaller or easier subproblems. So some of you might have heard about divide and conquer. So what we want to do is, rather than solving the big problem at once, we're going to split the problem into smaller ones. And step by step, we're going to solve that big problem. All right, that is the spirit of recursive functions. And sometimes these easier subproblems are actually the same problems, but in smaller or easier inputs. Then what we can do is, if the problem is small or simple enough, then we're going to solve it directly. And this is called base case in respect of computer science and recursive functions. And if the given problem is not small enough, then what we're going to do is divide the given problem into one or more simpler instances of the same problem, and pass these smaller problems to the function itself, assuming that it will perfectly manage the smaller problems. So what we need to be careful about is how we divide the given problem into smaller ones and pass those smaller problems to the function without thinking that it's going to work well or not. We just trust that it will perfectly manage the smaller problems. And the beauty of recursion is we solve just small problems and let the function handle the rest of it. All right, let me give you an example. How can you print a number in base 8? For example, what is 83790 in base 8? We know how to do this by hand, right? We write down this number here, and we divide this by 8, and we find the remainder, and we do the division again, and find the next remainder, and we keeps on doing this, and write the remainders in sequence, and that is going to be this number in base 8, right? We know how to do this by hand. And how can you implement this functionality with computer or Python? It is quite easy to find the last digit of a number n in base 8. As I told you, we just divide this number with this 8, and then we find out this remainder, right? And finding remainder in Python is simply using this percent operation. It will simply give you the remainder. And the remaining digits, after we calculate this remainder, what we get is n/n8. This will not think about the numbers after dot, like floating numbers, right? It will always return in integers. And let's implement this function together. So what we want to do is print some numbers in base 8 when we are given a specific number n. And what we do is, if n is larger than 8, we're going to print base 8 and pass the remaining numbers. Else, what we are going to do is print n%8. We put this extra parameter here, and this will print our numbers in base 8. All right. So what is this parameter means? I'll explain this part first. When we print some numbers in a row like this, then after this print function prints out this parameter, it changes the line. So when we want to print out the next one, 8, it printed out on the next line, and 9 on the next line, like this. However, when we put this parameter, pass this parameter to this print function, what it does is, rather than changing the line, it just remains there. And the next print function will print out the character or text given on the next position, like this. All right. So when we call this function, we'll print out we should not put else here. The number in base 8, right? So this is how we implement this print base 8 function. So what we basically did is we find out the base case. So the base case is this one. So if n is, so here the base case is n is smaller than 8. So when n is smaller than 8, we just print n. That's all we need to do. And if n is larger than or equal to n, then we divide this number by 8 and then pass this number, the remaining one, to the print base 8 function itself. All right. So this is the base case, and this is how we divide our big problem into smaller one. All right. So why does it work? Let's prove the functionality of print base 8 by mathematical induction. And here, K denotes the number of digits. So first, the base case is when K is 1. We have just one number of digits. And as I told you, this corresponds to the case where n is smaller than 8. In this case, print base 8 prints one digit correctly. And we want to prove that this will still work even when K is larger than 1 or n is larger than or equal to 8. And we make the inductive assumption that print base 8 works correctly for numbers with less than K digits. If we call print base 8 n, then it recursively calls print base 8 and /8, right? So this is the definition of our print base 8 function. But n/8 has K minus 1 digits in base 8. And by the inductive assumption, we assumed that this function works correctly for these numbers. So this will work correctly. Finally, we print out the last digit, right? Thus, it follows that print base 8 prints n in base 8 correctly. All right, so this is how we prove the functionality of this function using mathematical induction. All right. So up to this point, are there any questions? All right, let's move on. So let's implement factorial. So what is factorial? N factorial is simply n times n minus 1 times until we reach 1, right? So this is simple operation. And when we try to implement factorial, some of you might implement the factorial function in this way. And do you think this will correctly work or not? Let me know your opinion. All right, so why doesn't it work? Yes, you gave me the right answer. So when we try to call this function, what it does is, let's say when we call factorial 3, then what it's going to do is return, because n is 3 now, 3 times factorial n minus 1, that is 2. And this f2, when we call this f2 function, it will return 2 times f2 minus 1, that is 1. And f1 is going to be 1 times f0. And f0 becomes 0 times f minus 1. And it goes on and on. So it does not stop because there is no base case. So you guys are getting this right. And what about this one? Does it work well? think about it for a moment. I'll give you 30 more seconds to think about whether this one is correct implementation or not. All right, thank you for sharing your answers. Hayne explained gave the right explanation, because when we try to run this function, what it does is call the factorial and again. So it cannot reach this base case. So even though it has this base case, it cannot reach this base case because we are not decreasing n. All right. So this was pretty simple, right? Thank you for sharing your answers. And let's think about summing digits without a loop. So for instance, if we have number 2022, then summing digits might be 2 plus 0 plus 2 plus 2, and that is going to be 6. And how can you sum up all the digits without using any loops? Can you implement a function for this? So for example, let's say we have a function that receives a number so when some digits receive 2022, it's going to return 6. Some digits 2023, it's going to return 7. So can you implement this function? Think about it for a moment. But to give you a hint, when you try to implement this function, you can do similar things using percent operation and double slash operation. All right, let's have a look at how to implement this one. In fact, this one is from Jaeyoon. Let's first think about the base case. So when n is smaller than 10, this might be the base case. All right. Then what we're going to do is return just n. Because when we want to sum digits, a single number, and it's going to be just 8, right? And in other cases, if n is larger than or equal to 10, then what we are going to do is return n%10 plus some digits and /10. However, when you actually, you don't have to put else here, because when you call return here, then this function will end here. It will not go below this part, right? So you can just skip writing else. So you can save some indentation like this. So this one is from some of our students, one of our students. When you implement this function in this way, then it might be somewhat confusing at first. So what I suggest you is give some names to these values, right? So what I'm going to call this one is the last one, all right? So we are going to save the last one. And I'm going to call this one as all but last, all right? So we are going to pass this all but last to our sum digits function, and it will work correctly. We just assume that it will handle the rest of it. We just think about the base case, all right? So this is how we implement this sum digits function. And when we call sum digits, it's going to be 7 like this, all right? So any questions about this implementation? All right, let's move on. So one question is, why can we remove the else statement or else keyword? Let's talk about here. I told you that sum of any one-digit non-negative number is just that number. So that is our base case right here. And the sum of a number is the sum of the first digits, the first k-1 digits, plus the last digit. So that's what comes here. And the difference between these two implementations is just removing this else keyword. Because when a function meets or reaches return statement, it will not go below this part, right? So in the view of this sum digits function, it has only this block or this block. So even though we remove this else statement, because we have return here, it works as separating these two blocks, right? So that's why we can remove else keyword, because return finishes or terminates this function. So these two blocks are separated by this return keyword, all right? Let's move on. So that was about just normal recursive functions. And from now on, I'm going to talk about mutual recursion. So what is mutual recursion? The definition of mutual recursion is a recursive procedure or function is divided among two functions that call each other. So in our previous definition of recursive function, a function called itself. However, in the case of mutual recursion, these two functions will call each other like this. And I'm going to give you one example. A number, this number here is an integer, is even if it is one more than an odd number, right? So numbers alternates between even number and odd numbers. 1, 2, 3, 4, 5. So this one is odd, even, odd, even, odd. So they alternate, right? And a number is odd if it is one more than an even number, right? Because they are next to each other. And 0, let's say it is even. All right. And how can you define some functions that checks whether given numbers are even or not? Let's implement this function together. What we can do is, when we're given a number, if n equals 0, so this is going to be our base case. When n is 0, then we define that 0 is even. So we are going to return true. Otherwise, what we are going to do is return is odd. So we are going to check if this number is odd or not. When I finish implementing this function, this might be clearer. If n equals 0, that means this number is not odd, right? And what we're going to do is even and -1. All right. So this is, see, is even calls is odd, and is odd calls is even. So when we run some functions, some examples, it will return false and true like this. All right. So rather than tackling these big number, we just split or decrement this number into smaller ones and reach the base case. All right. So this is what a mutual recursion is. And I'm going to give you another example of mutual recursion. This one was quite simple, and in practice, we don't implement is even or is odd functions this way. We just use percent operation. That is much intuitive, right? So I'm going to talk about the LON algorithm. This LON algorithm is used to verify if a credit card number is valid or not. So how do we do this? So from the rightmost digit, which is the check digit, we move towards the left. And we double the value of every second digit. And if the product of this doubling operation is greater than 9, then sum the digits of that product. So when you see this definition, it might be somewhat confusing. So let's say we have 1, 3, 4, 7, 2, 9. So what we are going to do is we start from the rightmost digit. And we call this one as check digit. And we move towards the left side. And when we reach the even position number, we're going to double this one. So this will become 4. And when we reach or encounter even position number, we just pass. And when we encounter this number, we double this one. So what if this number was 9? And when we reach this number, we're going to double this number. It's going to be 18. And this is larger than 9, greater than 9. Then what we do is just sum these two numbers, and it's going to be 9. All right? So this is the first step of the learn algorithm. And what we are going to do is sum these numbers, 9, 3, 8, 7, 4, and 9. All right? So for example, if we have this 1, 3, 8, 7, 4, 3, all right, can you guys calculate the result of run algorithm when we input this number 138743? All right, thank you for sharing your answers. So let's calculate this one together. So for the first digit, what we're going to do is just let it remain 3, right? And when we encounter 4, because it's on the even position, we're going to double it, right? And 7, it remains 7. 8, it's going to be 16. However, it's larger than 9, so we are going to sum these digits. So it's going to be 7. And 3 remains 3, 1 becomes 2. And then we sum these numbers, that's going to be 30. So everyone is getting the right answer, I guess. And if the lump sum of a valid credit card number, so if this number is a multiple of 10, then that means this credit card number is valid, all right? And my question is, can you implement the learn algorithm? You need to use mutual recursion, as well as the sum digits we used before. You can modify the sum digits in some way. Then you can implement this learn algorithm. Try to think about how you can implement this learn algorithm. I'll give you like 3 minutes. So one hint is you need to process even position numbered differently from odd position numbered. And 3 minutes is quite short to implement this function. So even though you cannot implement this function in 3 minutes, don't worry about it. All right, let's implement the learn algorithm together. I told you that the example was 1, 3, 8, 7, 4, 3. So we need to process the odd position numbers differently from even position number, right? So what we're going to do is implement the schemes. We're going to implement 2 functions. One for odd position numbers, and the other for even position numbers. Okay. So let's define learn sum. So this is going to be a normal odd position numbers. So what we're going to do is, if n is smaller than 10, then we just return that number. All right. And what we are going to do when n is larger than or equal to 10, we are going to divide this number into 2 parts. So the last part, which is going to be n% 10, and all but last, which is n/10. And what we are going to do is return last plus, so here we are dividing 3 and the rest. And this rest is stored in this all but last variable, right? And we're going to pass this all but last to learn sum double. All right. And how do we define this learn sum double? So this one basically receives a number whose first number, so now this one goes to this learn sum double function, and the last digit was actually on the even position. So we need to double this number. All right. So what we are going to do is the same thing. Split this number into 2 parts. All right. And what we are going to do is we need to double this last digit, this one. However, if this one is larger than 9, for example, when it was 8, we need to double it, and it's going to be 16, and we need to add 1 and 6. And we know a special function for that, which is we implemented previously, this one. So we are going to call this sum digits function here. All right. And the next thing we need to do is, if this number is smaller than 10, then we just return this learn digit. right? However, if this number is larger than 10, for example, it has more than one digits like this, then we just removed 4 here, and all last here is going to be 1387. And for this one, we just need to do a normal lump sum. So what we're going to do is return ln digit plus, we're going to call the previous function, lump sum function, for this about last. Right? This is how we implement this ln algorithm. So when we call this lump sum function to our 138743, and it's going to return 30 as expected. So is there any question regarding implementation of this lump sum algorithm? So basically what we did was, when we have two different behaviors, we are going to implement two functions, and we're going to handle these two operations separately. That's the spirit of mutual recursion. All right, that was mutual recursion. And from now on, I'm going to talk about the differences between recursion and iteration. And you might say, what are the differences between recursion and iteration? You can do the same thing rather than doing recursion by iteration. So for example, we implemented recursion, we implemented factorial using recursive functions this way. So if n is smaller than 1, we just return 1. Otherwise, we're going to return n times factorial n minus 1. So this was how we implemented factorial, right? And we can implement this factorial function using iteration, the loop we learned. So in this case, what we're going to do is define two numbers, total and k. While k is smaller than n, we're going to increment k one by one. And we're going to multiply this k to total, right? So at first, k is 1, k total. K is 1, and total becomes 1 times 1. In the next iteration, k becomes 2. Then we multiply these 2 to k to total, and it's going to be 2. In the next iteration, k becomes 3, and we're going to multiply t times 3, which was 2 in the previous iteration. So it's going to be 6. So in this way, we can implement factorial using iteration. And in the end, we're going to return the total. So what are the differences between recursion and iteration? Mathematically, recursion is a relational equation like this. On the other hand, iteration can be expressed in this multiplication operation. All right? So mathematically, we can represent them differently. And another difference is we have two names for recursion. On the other hand, we have 4 names or 4 variables in the case of iteration. So we can do the same thing with smaller number of names when it comes to recursion. And we need to use more names in general for iteration. So is this the only difference? This might be somewhat confusing for some of you. However, when you learn computer systems or computer architectures, you might learn the difference between recursion and iteration. Recursion calls functions more than one time. So when you want to calculate factorial, let's say 5, it's going to call factorial quite a lot, like 5 times, around 5 times, right? However, when it comes to iteration, we just call this factorial function once. So recursion involves many function calls. And when you call many functions, they affect a memory called stack memory. You're going to learn the concept of stack memory in the computer systems or computer architecture classes. So sometimes this might be problematic. So in general, people recommend iteration. However, if the problem is quite simple and it does not involve many function calls, then people prefer recursion. So according to your application, you need to choose whether you are going to take the approach of recursion or iteration. All right. So that is another difference between recursion and iteration. If you can understand this concept, don't worry about it. When you go to computer systems and computer architecture classes, they will teach the same thing. And how can you convert recursion to iteration? Iteration is a special case of recursion. And can you convert the following recursive function into a iterative function? So I'll give you some minutes and try to convert this recursive function into an iterative function. Does anyone need more time to think about it? Okay, let's convert this function into a iterative one together. When you convert a recursive function into iteration, you need to figure out what state must be maintained by the iterative function. So the answer might be this one. We need to keep the state of the digit sum, right? And we need to do this job again and again while n is larger than 10. So basically, in this case, we cared about the base case. And this base case was when n was smaller than 10. However, in this iteration, this is the opposite, right? We do this when n is larger than 10. And we're going to do the same thing. Split the number like less than n. You could call this all but last, but because of space limit, I just called it n. So we're going to split these two numbers like this. And then to the digit sum, we're going to add this last. And after this loop, we're going to return this digit sum variable. All right. So this is how we can convert a recursion into an iteration. And in the opposite way, we can convert iteration into recursion. All right. And in the previous slide, I told you that iteration is a special case of recursion, and recursion is a special case of iteration. And the state of an iteration can be passed as an argument. So here, we're passing these two states into a function itself as arguments or parameters. All right. So when we are converting recursion into iteration, you need to think about what state you need to maintain. On the other hand, in the case of converting iteration into recursion, you need to think about what parameters or what states to pass as arguments or parameters. All right. So you need to think about those two things. And I'm going to talk about tree recursion. So most of you guys might know what Fibonacci numbers are. So Fibonacci numbers are very simple. So the first Fibonacci number is 0, and the second Fibonacci number is 1. And how we construct the next Fibonacci number from the previous two, it's going to be 1. Summing these two, the next Fibonacci number is going to be 2, 3, 5, 8, 13, 21, like this. So this is Fibonacci, these are Fibonacci numbers. And can you implement a function that returns Fibonacci number like this? And you can implement this function using recursion. All right. Think about it for, let's just implement this together. I guess we're running out of time. So we're going to implement this Fibonacci number returning function. So what are the base cases? Can you guys guess the base cases? So from these two statements, we can directly see that these two cases are base cases. So we're going to implement these two parts. So when n equals 0, we're going to return 0. If n equals 1, we're going to just return 1. Otherwise, so these two are base cases. Otherwise, what we are going to do is return Fibonacci number plus 3 and minus 2. This is very simple, right? it's going to return Fibonacci numbers correctly, like this. However, this one entails some problem. So let's see what the problem is. When n is small, this is quite fast. However, let's see what happens. So we are trying to print out Fibonacci number 34, and it's taking longer and longer time, like more than 10 seconds. And when n is larger than 35, it's getting a lot slower, like more than 24 seconds. So it's taking quite a lot of time, right? So let's stop here. So one of the problems of this naive implementation of Fibonacci number is it takes too much time. So why is that? This is called, so our implementation becomes very slow when n is larger than 35. So when we see what happens when we call Fibonacci 40, it's going to call Fibonacci 39 and Fibonacci 38. And Fibonacci 39 will call Fibonacci 38 and Fibonacci 37. What's happening here? So Fibonacci 39, let's say Fibonacci 38 comes up here, here, here. And 37 appears here, here, here. And 36 here, 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 right? So we are doing the same computation again and again. Specifically, when we are computing Fibonacci number 40 or Fibonacci number 41 minus k, they are computed Fibonacci k times, meaning that so many redundant computations are there. So the lesson or takeaway from here is blindly applying recursion is not always appropriate. And as I told you in the previous slide, that this will cause stack memory overflow error. Stack memory will be full because we are calling too many functions. All right. And how can you resolve this redundancy in computation? Any suggestions? Can you guys guess how can you resolve this issue? Yeah, Hein, Hong은, and Seungjae gave some ideas. And storing some computed values might resolve this issue. Yeah, that is correct. Let's implement that functionality together. So rather than calling this function again and again, what we are going to do is store the computed results. Or we can turn this recursive function into iteration. So by converting this function into iteration, we can store the computed values. So let's say the Fibonacci numbers, the first one and the second one is 1 and 0 and 1. And for I in range 2 to n, what we are going to do is append the new number So what we are basically doing here is adding the last two numbers inside here. And that is going to be the new Fibonacci number. And we're going to return the last number like this. All right. So let's see what happens. We call. So does everyone understand this implementation? So this -1 indicates that the last item, and this one indicates the second last item. And adding to these two numbers, the last item, the second last item, gives next Fibonacci number. All right. So when we run this code, this one is much faster. All right. So as I told you, according to your application, you need to think about what approach you are going to take, recursion or iteration. I'm going to give you another example of recursion. Some of you might have heard about Tower of Hanoi. This is what we are going to do. Basically, what we want to do is move these plates. Let's say this one is destination, and this one is spare, and this one is source. So we have 3 poles and a number of plates like this. Let's say N plates. And we want to move all the plates in the source pole to the destination pole. However, the rule is like this. You cannot put larger plate on smaller plate. You cannot do this. All right. And how many times you need to move plates? What is the minimum number of moving that you need to do to move all these plates, N plates, from source to destination following this rule? Larger plates cannot be on top of smaller plates. In fact, we can solve this problem quite easily using recursion. So what we can do is, so what we are going to implement is move disk 1 from A to C, move disk 2 from A to B. So we want to print out the sequence of actions we need to do. Okay, so this is what we want to implement. Then how do we divide this given big problem into smaller ones? So how would you divide this problem into smaller ones? So let's have a look at what we can do. We're going to divide this problem in this way. Let's say we have N plates or N disks. And what we want to do is we first move N-1 disks into spare pole. All right. So we are moving these N-1 disks, the top N-1 disks, to spare pole. And next, what we are going to do is move this nth disk to destination. And then we're going to move this N-1 disks to the destination. So this is how we divide this problem. And we are not going to think about how we can do this, but we will just let our function perform this on its own. So that's the beauty of recursion. So in fact, this is the implementation. So the base case is when we have just one disk, then what we are going to do is move this disk 1 from source to destination. That's all we need to do. So if we have just one disk, then the problem becomes very, very simple. We're just moving that disk from source to destination. What if we have more than one disk? And as I told you, we're going to first move the n-1 disks from source to spare. Here, this is the position of destination, but the destination of n-1 disks is the spare pole. All right. And then we're going to move. So the first line, this line, corresponds to the second picture here. We're moving n-1 disks to the source pole. So this source pole is destination of this n-1 disks. Okay. And then we're going to move the largest disk from source to destination. So this corresponds to this picture. And lastly, what we need to do is move this n-1 disks from source to destination. Right? That's what this last expression is doing. So we are moving the n-1 that is positioned as spare to destination. So this is how we solve HANOI. All right. So when we use recursion, we can solve this problem quite easily. However, when we try to solve this problem with iteration, it becomes very, very complicated. So this is the right place to apply recursion rather than iteration. All right, this one is a coding problem. This one actually appeared in the coding interview of Facebook, MS, Amazon, and Airbnb. Let's say you're partitioning a staircase, 계단, and it consists of n steps to the top. And the maximum part you can take each time is m. Then in how many distinct ways can you partition this staircase? So for example, let's say we have 6 steps and the maximum step you can take is 4. Then what we can do is first take 2 steps and next you take 4 steps and it's going to be 6 steps. So this is one way of partitioning these staircases. And the next case is take 1 step, and 4 steps. And 3, 3, 6, 1, 2, 3, 6, like this. So in how many ways can you partition this staircase, taking the maximum step of m? Try to implement this function on your own. We are going to discuss this problem in the next class. All right. Let's call it a day. If you have any questions, you can stay here. Otherwise, you can leave now. Thank you for your participation.